Humans have always been obsessed with speed. From the first runner to the fastest jet, we push the limits. But what if we could reach the ultimate speed, the one cosmic speed limit that governs everything? I've got a question for you, one that physicists and dreamers have asked for a century. What would we actually see if we were traveling at the speed of light? It's a question that unravels the very fabric of space and time, and the answer is far stranger and more beautiful than you can imagine. Before we begin our journey, let's get one crucial fact out of the way. According to Einstein's special relativity, nothing with mass can ever truly reach the speed of light. As an object accelerates, its mass effectively increases, and the energy required to push it faster and faster grows exponentially. To reach light speed, you'd need an infinite amount of energy. It's the universe's ultimate no trespassing sign. But here's the fun part. We don't need to break the law, we just need to bend it. We can get unimaginably close, say 99.999% of light speed, and that's more than enough to twist our view of the cosmos in glorious, brain-bending ways. So, buckle up, we're about to take a ride on a beam of light. As we accelerate, the first and most dramatic change happens to the stars around us. The familiar sprawling star field begins to warp. Stars that were once scattered across our view, above, below, to the sides, all seem to migrate forward, crowding into a brilliant, concentrated cone of light directly in front of our ship. This isn't an illusion. It's a fundamental consequence of our speed called relativistic aberration, also known as the headlight effect. It's as if the entire universe is being squeezed into a single dazzling point on our windshield. The darkness of space is no longer all around us. It's now, mostly, behind us. At the same time, the colors of the universe begin to shift dramatically. This is the Doppler effect, but for light. Just as a siren's pitch rises as it approaches you, the light waves from stars ahead of us are compressed, shifting their color towards the blue end of the spectrum. This is called blue shift. A familiar yellow star like our sun would appear bluish-white. A red giant would look yellow. Blue stars would shift into the invisible ultraviolet range, and then, even further, into X-rays and gamma rays. Meanwhile, looking back, the opposite happens. Light from stars behind us is stretched out, or redshifted. They fade from red to infrared, then to microwaves, and eventually slip into total blackness. The sky ahead becomes a harsh blue-white glare, while the view behind is a growing void. This creates a serious problem. That forward cone of light, now packed with blue-shifted starlight, becomes dangerously bright and energetic. Even the faint, harmless light from distant galaxies, when compressed and energized by our speed, transforms into a high-intensity beam of radiation. It would be like driving your car directly into a cosmic spotlight, powerful enough to vaporize your ship. Any near-light speed travel would require some form of unimaginable shielding just to survive the view. Now, what about objects closer to us? You might expect them to look squashed in the direction of travel, due to an effect called length contraction. And they are, in reality. But what is different? As we zip past a stationary cube, for example, we wouldn't see it flattened. Instead, it would appear rotated. This bizarre visual trick is called the terral rotation. It happens because the light from the back of the cube has to travel further to reach your eyes than the light from the front. This time delay in the photons arriving at your retina creates the illusion of rotation. So, instead of a universe of flattened pancakes, you'd see a universe of strangely swiveling objects. This same principle of length contraction affects our perception of distance. The space ahead of us would seem incredibly foreshortened. A journey to a star 4 light-years away wouldn't just feel faster. The distance itself would appear to shrink from your perspective. A vast star system you're racing toward might look as compressed as a nearby city. It's a world where geometry and the timing of photons conspire to create a landscape that is both real and illusory, a direct consequence of your motion through space-time. And what about time? Aboard our ship, everything would feel perfectly normal. Your heart would beat at its usual rhythm, your watch would tick away the seconds just as it always does. This is the principle of relativity. Your own frame of reference always feels normal. But if you could look back at a clock on Earth, you'd see its hands crawling at a snail's pace. From Earth's perspective, your clock is the one that's slow. This is time dilation. Even more mind-bending is the relativity of simultaneity. Two events that happen at the same time for an observer on Earth would happen at different times for you. The very idea of a universal now completely breaks down. Let's look wider, at the biggest thing we can see, the cosmic microwave background, or CMB. This is the faint uniform afterglow of the Big Bang, a sea of microwave radiation that fills all of space. For us, it's a key to understanding the universe's origins, but at near light speed, it becomes another hazard. The CMB in front of us would be intensely blue-shifted, transforming from gentle microwaves into a blinding, high-energy torrent of gamma rays. Behind us, it would be red-shifted into oblivion, making the sky in our rearview mirror colder and darker than the deepest void, a near absolute black, as we push our ship even closer to the ultimate limit, 99.9999% of light speed and beyond. All these effects intensify. The forward-facing cone of light narrows into a single needle-bright point. The universe of stars, galaxies, and cosmic radiation is compressed into an infinitesimally small, infinitely bright tunnel directly ahead. Everything is in front of you. Behind you there is almost nothing. Just absolute, profound, and silent darkness. And here we finally reach the absolute limit. What would you see at the speed of light? The answer is nothing. Because to travel at light speed, you must be light. You must be a photon. And for a photon, time does not pass. From the moment it is emitted from a distant star to the moment it is absorbed by your eye, a photon experiences no journey, no duration, no before and after. Its entire existence across billions of light years happens in an instant. There is no time to form a view. The concept of seeing becomes meaningless. So, let's ease off the throttle and return to the realm of the possible. As our ship decelerates, the universe gracefully unfolds back into its familiar form. The blinding point of light ahead softens and expands. The tunnel of stars relaxes, widening as constellations repopulate the sides of our view. The harsh blue shift subsides, and colors bleed back from their violent, energetic state into the familiar, gentle palette of reds, yellows, and whites we know. The profound darkness behind us gives way to light. The redshift that had stretched starlight into invisibility releases its grip, and the familiar glow of the Milky Way and distant constellations emerges from the blackness, reclaiming the rear view. The universe, once warped by our incredible velocity, returns to a state of serene, expansive beauty. We're in the same ship, looking with the same eyes, but the universe we perceive is entirely dependent on our motion through it. Speed doesn't just change how long it takes to get somewhere, it fundamentally sculpts the geometry of space and the flow of time. Space-time itself dictates how different observers will disagree on the most basic concepts of distance, time, and even what happens when. So, to recap our journey, traveling near the speed of light means seeing a blinding blue-shifted halo of stars ahead, a star-starved, red-shifted void behind, and nearby objects that seem to swivel and rotate as you zip past them. It's a universe both beautiful and hostile, governed by the strange and counterintuitive rules of relativity. This might all sound like a wild thought experiment, but these ideas are tested and confirmed right here on Earth every day. Our most precise instruments, from atomic clocks on GPS satellites to detectors in physics labs, must account for relativistic effects to function correctly. We don't chase light in starships, but we do chase its consequences with precision and patience. In massive particle accelerators, we push subatomic particles like electrons and protons to 99.99999% the speed of light. We see their effective mass increase and confirm the energy requirements predicted by Einstein. We also see time dilation in action. Short-lived particles called muons, created when cosmic rays hit our atmosphere, travel so fast that their internal clocks slow down from our perspective, allowing them to survive the journey to the Earth's surface. A journey that should be impossible given their short lifespan. Experiment perfectly matches theory. Even the sky above us serves as a natural laboratory. High-energy cosmic rays, particles accelerated to near light speed by distant supernovae, and black holes, constantly slam into our upper atmosphere. The showers of secondary particles they create carry the unmistakable signature of time dilation and length contraction, providing daily proof that the universe really does work this way. It's helpful to picture the universe as setting a constant metronome, the steady ticking of light itself. As your speed through space increases, your perception of that rhythm changes. The beats you are moving toward. The light waves ahead seem to cram together, ticking faster and faster. The beats you are leaving behind stretch apart, fading into a slow, deep rhythm. Your vision, your very perception of reality, is forced to keep time with the laws of relativity. From the outside, an observer watching our ship fly by would see it as strangely distorted and foreshortened, its internal clock running incredibly slow. But from the inside, our seconds would feel perfectly ordinary, and it would be the outside universe that appears warped. It's the ultimate lesson of relativity. There is no single privileged viewpoint. There are only different perspectives, all equally valid, woven together into a single four-dimensional reality sculpted by motion and light. So, what would we see at the speed of light? The journey has shown us the answer is twofold. Approaching that speed, we'd witness a universe transformed, a blue-white tunnel of light ahead, an abyss of darkness behind, geometry playing tricks on our eyes, and clocks that refuse to agree. But at the exact speed of light, the journey and the destination become one. There is no time, no distance, and therefore, no view. For light, there is no time to see.